Hey guys, this is Professor Janacek. I want to talk to you about a convergence test, specifically the limit comparison test. Now don't get this confused with the comparison test. In this case, we are going to be looking at a limit. I'm not going to go over the details of why this works. I just want to go over how to determine convergence or divergence using this test. Now we are going to be looking at a limit, specifically the limit of our given series, a sub k, over some b sub k's that we'll have to find. We want this limit to be both positive and finite. Now, if that's the case, once we find the b sub k's, if those converge, then the a sub k's also converge. But if the b sub k's diverge, then the a sub k's will also diverge. Let's take a look at an example or two. Suppose we have the sum, as k goes from 1 to infinity, of k to the fourth minus 2k squared minus 3 over 2k to the sixth minus k plus 5. Now what we're going to start with is the limit, as k goes to infinity, of the a sub k's, that's our given sequence, over some other sequence. Now, these are my a sub k's. We have to figure out what the b sub k's are. What I notice here is that the leading coefficients, k to the fourth over 2k to the sixth, that actually reduces to a nice little ratio. So let's use that as our b sub k's. That's 1 over k squared. Again, we had to choose those, but I was looking at the leading coefficients there. I can simplify this a bit, multiply by the reciprocal of that denominator, make sure you continually write that limit notation in the front. If I distribute this out, we get the limit, as k goes to infinity, of k to the sixth minus 2k to the fourth minus 3k squared over 2k to the sixth minus k plus 5. Now to take this limit, I do not need to use L'Hopital's rule. I can simply use the nice little technique for whenever we have a polynomial over a polynomial, or a rational expression. I'm going to multiply by 1 over k to the sixth. I choose this k to the sixth because it's the highest power in the denominator. Distribute that out, and we have the limit, as k goes to infinity, of 1 minus 2 over k squared minus 3 over k to the fourth over 2 minus 1 over k to the fifth plus 5 over k to the sixth. Now you'll notice, as k goes to infinity, that having a k squared in the denominator, or k to the fourth in the denominator, k to the fifth, or k to the sixth in the denominators of those little expressions make all of those go to 0. So we end up with 1 minus 0 over 2 minus 0, which is simply 1/2. And I notice that this is both positive and finite. The other thing we need to look at is the series of b sub k's. So the sum as k goes from 1 to infinity of 1 over k squared. Well, this is p series. With the p-value being 2, which is greater than 1, which means that this series of b sub k's converges. Thus, my original series of a sub k's also converges. Let's take a look now at the sum as k goes from 1 to infinity of 1 over the square root of k squared plus 1. We'll start by looking at the limit as k goes to infinity of my a sub k's. That's what was given, 1 over the square root of k squared plus 1. Remember, these are the a sub k's. We have to find some b sub k's to go in the denominator. Again, looking at just kind of my leading coefficients, in the denominator we have the square root of k squared, which is simply k, so we can write 1 over k, and I think that will simplify things nicely. Now this limit, as k goes to infinity, is of 1 over the square root of k squared plus 1 times k over 1. We can simplify this a bit. We have the limit as k goes to infinity of k over the square root of k squared plus 1. In this case, I'm going to go ahead and multiply this by 1 over k over 1 over k. It's similar to the polynomial trick, or the rational expression trick that we looked at in the first example. If I distribute those 1 over k's, I get 1 over k times the square root of k squared plus 1. We can do a little bit more with that. I'm going to actually put that 1 over k inside the radical. Putting it inside the radical makes it 1 over k squared times k squared plus 1. Now I'll distribute that inside the radical. So inside the radical, there in the denominator, we have 1 plus 1 over k squared. Now, as k gets really large, 1 over k squared goes to 0. So I think we're ready to evaluate this limit. That gives us 1 over the square root of 1 plus 0, which we can see is simply 1. Notice that this is both positive and finite. That's exactly what we want. We also need to look at the series of our b sub k's. So the sum as k goes from 1 to infinity of the b sub k's, which are just 1 over k. Again, this is a p-series with our p-value equal to 1. If p is equal to 1, then this diverges. So our b sub k's diverge, which means our original series of A sub k's also diverge. Enjoy!